Welcome to session 2. Today we'll be looking at polar molecules and intermolecular forces. By the end of this session you should be able to identify whether a molecule is polar or non-polar, understand how London dispersion forces, permanent dipole to permanent dipole interactions and hydrogen bonding arise, and then be able to relate the type of bonding present to the properties, the melting and boiling point, solubility, viscosity of different molecules. And finally, we're going to look at hydrogen bonding between water molecules and show how that results in ice being less dense than water. What is a polar molecule? A molecule can be described as polar if it has a permanent dipole. Now, we're not talking about just in a bond. In our last session, we looked at polar bonds, for example, hydrogen and chlorine. Chlorine is a much higher electronegativity than hydrogen. Electronegativity of chlorine is 3.0, hydrogen is 2.2. So the electrons in the bond are closer to chlorine, and that gives it a slightly negative charge compared to hydrogen, slightly positive charge. We have a permanent dipole in that bond, but we have to see if this applies to the whole molecule. And the spatial arrangement of polar bonds, the shape of the bonds around a molecule, can result in it being polar or not. So we'll look at some typical examples together. Is this molecule polar? Your first step, are there polar bonds in the molecule? And then we'll have a look at the shape and see what effect that has. So let's go back to that HCl. We said hydrogen was slightly positive, chlorine was slightly negative, and that's a polar bond, but in fact we have a whole molecule there. And that charge difference exists across the whole molecule. There is a dipole, a permanent dipole across the whole molecule. I could draw a little line through this molecule. One half of the molecule is a different charge from the other. Two poles, dipole, and it's permanent. And it's permanent because that difference in electronegativities between those two atoms is permanent. This time we'll look at water, 3-element molecule, and if we think about the electronegativity values, we can answer our first question: are the bonds in the molecule polar? Yes, they are. Oxygen will be slightly negative, hydrogen slightly positive. Now we think about the shape. Is there a charge difference across the whole molecule, a permanent dipole across the whole molecule? Well, I could draw a line through that there. And the top part of the molecule is slightly negative, whereas the bottom part is slightly positive. Over this whole molecule, the one side of it is slightly negative and the other side is slightly positive. There is a permanent charge difference, a permanent dipole across this whole molecule. This time we'll look at carbon dioxide, and electronegativity of carbon is 2.5, oxygen is 3.5. So again we have polar bonds. But does that make the whole molecule polar? Well, we have to think about the shape here. And again, if we're thinking about drawing a line through the molecule, do we have one bit that is different from the other? No, there would be no difference here. Negative, positive, negative, negative, positive, negative. That's the same both sides. Putting our line through the molecule the other way, we can see that the bond polarities are equal and opposite. They're going to cancel each other out. There will be no charge difference across the molecule. No dipole across the molecule. So although individual bonds are polar, the molecule does not have a dipole across it. It is not polar. This is not a polar molecule. So here we have ammonia, and again we can check our electronegativity values and find that the nitrogen will be slightly negative, hydrogen slightly positive, and we can think about putting lines through the molecule again. Is one part of the molecule a different charge from the other? Yep, the top part is slightly negative, the bottom part slightly positive. Remember, this is a trigonal pyramidal structure, so that nitrogen stands tall, proud at the top. So we do definitely have a charge difference across this molecule. This time we have a tetrahedral molecule, carbon tetrafluoride, and looking at the electronegativity values, we can see that the fluorine is slightly negative compared to the carbon, which is slightly positive. Using a line through the molecule, we can see that it doesn't matter what way we put it, that there is no charge difference across the molecule. If we change just one of the fluorines though for a hydrogen, we can see hydrogen would be very slightly positive compared to the carbon. So we'd have our delta positive up there. Our fluorines are delta negative. Now when we're looking at this molecule, there is quite clearly a charge difference across the molecule, a permanent dipole. So this molecule is polar. Other things to look out for, if you see hydroxyl groups, OH, NH, these are going to signify polar parts of a molecule. You're always going to have some polarity if you have hydrogen bond to oxygen, hydrogen bonded to nitrogen. And the more of these groups there are in the molecule, the more polar it will be. If, however, you just have a hydrocarbon, that would not be considered polar at all. So hydrocarbon, not polar, hydroxyl, NH in your molecule, there will be some polarity there. Polar molecules have a permanent dipole across the molecule, and this charge difference across the molecule means they can actually interact with electric fields. And in this video, we'll show it being deflected by a charged balloon. Now it's shot in slow mode just to emphasise what happens. You could do this with a charged ruler as well. I didn't have one handy, so I was just rubbing the balloon in my head. And you can see that nice curve deflection of the liquid there as it's attracted towards the statically charged balloon. Now any polar liquid, a fine stream of any polar liquid would behave in the same way. So why is it important to know if a molecule is polar or not? Well, we have different properties depending on if we have a non-polar molecule or a polar molecule, and that's really down to different intermolecular forces, or we say IMF for short. All of these intermolecular forces come under the heading van der Waals forces, but we have three key types. London dispersion forces will have between all monatomic elements, all molecules. They're always there in the background. But when we have polar molecules, we have another two possibilities: permanent dipole interactions, or hydrogen bonding. And we're going to take a quick look at how these three intermolecular forces arise. London dispersion forces are caused by the movement of electrons. Helium here has 2 electrons, but what we find, because these electrons are always moving, sometimes they'll gather at one side. Now this is only temporary because the electrons are always moving about all over the place. They're always moving around everywhere, but it just so happens that at one point in time they're at that side of the atom or molecule. Well, now we've got a charge difference in this molecule. We have a slightly negative side here and a slightly positive side here. Along comes another helium atom, and its electrons are zooming about all over the place, but they find that because one side of the other helium atom is slightly positive, its electrons are pulled over to that as well. They are attracted there. So we now have a dipole in this atom as well, a temporary dipole, but it's been induced by the other atom. It didn't happen on its own, it was induced. We then have a force of attraction between these two oppositely charged dipoles there, a temporary dipole interaction, and that is a London dispersion forces. Now this temporary dipole interaction is caused by the electrons. And the more electrons there are, the bigger the charge difference will be, and so the stronger the temporary dipole interaction will be, the London dispersion forces. So more electrons gives rise to stronger London dispersion forces. So comparing neon to helium, more electrons in neon, so we'll have a stronger force of attraction, stronger London dispersion force between atoms of neon compared to helium. The stronger London dispersion forces between the neon atoms mean that neon has a higher melting point and boiling point, but higher melting point I'm shown here, than helium. Now, these London dispersion forces are very weak. We've still got really low melting points for these two, but it is making a difference. And if we have bigger molecules with a lot more electrons, then we see much higher melting points. But these are weak forces of attraction, the London dispersion forces, because they're temporary. Those electrons will not stay in that position. They're going to repel each other, they're always moving, and when they move, the force will be broken. And it doesn't take much energy to break the force. So London dispersion forces exist between all molecules and all monatomic elements. But with polar molecules, there are additional forces of attraction between the molecules. One of these is permanent dipole interactions. So in hydrogen chloride here, we have a permanent dipole across this bond, and because it is just this bond that makes a molecule, we have the polar molecule as well. We could split that in two and say one part of the molecule was different from the other. What happens then is when we have the molecules close together, there's an interaction between the opposite ends of the molecule. The negative part is attracted to the slightly positive part of the other molecule. And this is a strong force of attraction, stronger than London dispersion forces anyway. It takes more energy to break this force of attraction than it would to break the interaction between non-polar molecules of similar number of electrons. Similar number of electrons, we've got similar London dispersion forces. But this is an additional, stronger force of attraction than the London dispersion forces. Our final intermolecular force is hydrogen bonding. And this is a special type of permanent dipole interaction. It only happens when we've got oxygen bonded to hydrogen, nitrogen bonded to hydrogen, or fluorine bonded to hydrogen within a molecule. And that gives rise to strong forces of attraction between molecules. So with water here, the slightly negative end of the molecule can interact with the slightly positive end of the molecule with a neighbouring one. So we end up with these strong forces of attraction between these two molecules. And this is still happening in the same way as the permanent dipole interactions, but because it's so strong, it gets a special name, hydrogen bonding. And we get hydrogen bonding between the molecules. Again, if there's oxygen bonded to hydrogen, nitrogen bonded to hydrogen, or fluorine bonded to hydrogen. And it's because the electronegativity of these three elements is so high compared to hydrogen, we get a very, very polar bond there and leading to a very polar molecule. So now we'll look at some of the different properties of polar versus non-polar molecules. The first one is solubility. If we have a polar molecule, for example, ethanol will be soluble in water because the hydroxyl group in ethanol can make hydrogen bonding with the water molecule. They'll mix quite happily, they're soluble. So ethanol is soluble in water. If we compare that to ethanol being soluble in something like hexane, hexane is non-polar. It won't be as soluble in the hexane. If we had a non-polar molecule like iodine, however, it's not polar because it's a pure covalent bond. There's no charge difference across the bond, so there's definitely no bond polarity, which is the first thing we need for a polar molecule. So it's knocked out the first hurdle. Iodine is way more soluble in non-polar solvents because it is non-polar. We can dissolve iodine in water, but it's really not soluble. It goes this kind of browny red colour, as you'll have seen, whereas if we put it into a non-polar solvent, we get a lovely purple solution. So a rule of thumb is like dissolves like, but you can't say that in your answer. You'll get no marks from SQA if you put that in your answer. But keep that in your head. Like dissolves like. A non-polar solvent is good for non-polar molecules. Whereas for a polar molecule like ethanol, we need a polar solvent like water to dissolve it up. And the more hydroxyl groups a molecule has, the more polar, and so the more soluble it will be in water. And if I could keep replacing these hydrogens here with hydroxyl groups, I would be making this more and more polar, more and more soluble in water. And that's something that comes up in multi-choice questions. Which of these is most polar, or which is most soluble in water? The one with the most hydroxyl groups will be most soluble. So what about viscosity, another property? Viscosity is how easily a liquid flows. And the more polar a molecule is, with more hydroxyl groups, more nitrogen and hydrogen, the more viscous it will be. Why? Because there's stronger forces of attraction between the molecules. So it's a thicker, gloopier liquid. Think about honey compared to water. Honey is very gloopy, very viscous, compared to water, which is a lot more runny. It flows more easily. But the less polar a molecule is, the less viscous it will be because we've weaker forces of attraction. So if we have something like hexane compared to hexane-1-ol, the hexane-1-ol will be more viscous than the hexane. And the more hydroxyl groups there are, the more viscous it will be. The more polar, the stronger the intermolecular forces between molecules. Volatility is about how easily a liquid evaporates, how easily it goes from liquid into gas. This time, if we have our polar molecules, so we're looking for OH, NH in the structures, the more polar they are, the stronger the intermolecular forces, be it permanent dipole, or in the case of these ones here, hydrogen bonding between molecules, the stronger that is, the less volatile these will be. Whereas if we have non-polar molecules, they'll only have weak London dispersion forces between the molecules, and so they are going to be a lot more volatile. If we compare molecules with the same number of electrons, has to have the same number of electrons or similar, so we get similar London dispersion forces between the molecules. If we compare them, then the ones that are polar are less volatile because of the stronger forces of attraction between the molecules compared to the non-polar molecules with the weak London dispersion forces between the molecules. It takes less energy to break these, so they are more volatile. They will evaporate more easily. Next property is melting and boiling points, and these are directly linked to the strength of the intermolecular force. Now, if we're just looking at London dispersion forces, as the atoms or molecules get bigger and there are more electrons, there's stronger forces of attraction between the molecules, so it takes more energy to break that, and we end up with higher melting and boiling points. But it follows a fairly linear trend. In this plot, we're showing the trend in boiling points for hydrides down a group. And the red ones here, we're starting with group 4, carbon hydride, silicon hydride, germanium hydride, tin hydride. And you can see as we go down the group and we're getting more electrons in the molecule, the boiling point is getting higher and higher. And it pretty much follows a linear trend. You get a best fit line through that, and it's fairly linear, that relationship. But when we look at the other groups, group 5, group 6, group 7, we see that the first member is really enormously high. These are all really high compared to the rest. The rest of them follow that nice linear trend. So we go down the group, stronger London dispersion forces between the molecules because there's more electrons, but over at this end, they're way higher than they should be. If we're looking at group 7, hydrogen fluoride, if that was following the same trend, then we would really be expecting the boiling point of hydrogen fluoride to be down here somewhere. But it's not, it's way up here. And that's because there is hydrogen bonding between the molecules of hydrogen fluoride. And this is such a strong intermolecular force. Let's get my little dipoles in. This such a strong intermolecular force. It causes a huge leap above what is expected for the boiling point. And it would be the same for the melting point. So melting and boiling points are much higher for polar molecules and for ones that have particularly polar with hydrogen bonding between the molecules. And we'll get hydrogen bonding between the molecules when we have hydrogen fluoride here. Group 5, we have ammonia. NH3 is our first member. Again, hydrogen bonding between molecules there. Group 6, our first hydride would be water, H2O. Again, really strong hydrogen bonding between the molecules for water as well. And that causes this big leap in the boiling points. It's melting and boiling points, but here we're looking at boiling points. This hydrogen bonding between water molecules results in a very sort of spread out crystal structure when water solidifies. So solid water is a lot less dense than liquid water because as it solidifies, these hydrogen bonds fix the molecules in place and the structure is less dense than in liquid water where the molecules are still moving more around each other or jiggling around each other. So we've looked at how to identify a molecule as polar or non-polar. Check if the bonds are polar and then check the shape of the molecule. Is there a charge difference across the molecule? And the key things we said to look out for was OH, NH, FH. These groups in a molecule will tell us there is polarity in that molecule. If we just have hydrocarbons, they are not polar. London dispersion forces arise because of the random movement of electrons. More electrons in an atom or molecule, you'll have stronger London dispersion forces between the molecules, between the atoms, and that gives rise to higher melting and boiling points the more of the electrons there are. Permanent dipole interactions, that's when we have a polar molecule and we have a fixed charge difference across the molecule. So we have strong interactions there. Hydrogen bonding is a very strong version of permanent dipole interactions, where we have hydrogen bonded to oxygen, nitrogen or fluorine within the molecule. And we then have hydrogen bonding between the molecules. Hydrogen bonding is the strongest intermolecular force. Now, comparing these to covalent bonds or ionic bonds, they are much weaker, but hydrogen bonding, compared to London dispersion forces, a much stronger force of attraction between the molecules. And that means if we have hydrogen bonding between molecules or permanent dipole interactions, we will have higher melting and boiling points. We'll have good solubility in polar solvents like water. We'll be very viscous, and we looked at the volatility as well. These molecules, polar molecules, are not volatile. Compare that to molecules where we just have weak London dispersion forces between the molecules. We have lower melting and boiling points. We're only soluble in non-polar solvents. Not very viscous because there's weak forces of attraction between the molecules, so the molecules flow apart quite easily. And volatility is high. They evaporate very easily because it doesn't take much energy to break the forces of attraction, the weak London dispersion forces between the molecules. Hydrogen bonding between water molecules results in ice being less dense than liquid water, because in the solid state the molecules spread out and form these patterns, this crystal structure with quite spaced out molecules of water, whereas in the liquid things are much closer together. So if any of this is unclear or you want more details or want to ask questions in the webinar, you can fill out our form and try and get your questions in ahead of time. That gives us a chance to look them over and be ready to answer your questions in our live session.